setup. So we were discussing digital signal processing. So we started with the lecture number 3, which was about waveforms. What are the different kinds of concepts which are important in periodic waveforms? We looked at amplitude, frequency, and things like that. So that was to give you an intuitive understanding of what are signals and what are digital signals. And in the 4th lecture, we discussed about yes. So what are time series? Basically, it's just a signal which has ordering information or timing information also. It is preserved there. Then we saw what is the concept of sampling and quantization, that an analog signal or a real-time continuous valued signal, continuous in time as well as continuous in values. Such a signal, if you want to save it into our digital computer, then we have to first sample it in time and quantize it in values, so that I get discrete values, and each value is quantized to finite precision. And okay, these things were simple. Now, coming to the concept of convolution. So what is convolution? Convolution means you all have studied about linear time invariant systems and systems which are linear. I think I gave an intuitive understanding. Systems which are linear, which means if I scale my input by some factor, my output also gets scaled by the same factor. That is linear system. And time invariant system means if the same input comes at a later time instant, my response or the output also gets shifted by the same time instant, same amount of time. The output remains same, just shifted by the same amount of time. That is a linear time invariant system intuitive understanding. And to characterize these systems, we can simply see what is the response to an impulse or to a canonical delta function. Whatever is the response, using this response, we can construct the response to any arbitrary input, right? Because any arbitrary input can be written as a linear combination of canonical delta functions. Therefore, my output also is a linear combination of the impulse responses, as you can see here. As you can see here. So my output is a linear combination of the impulse responses. This was the intuitive understanding of convolution. And we looked at the visual understanding, that how we have an input signal X, which is a series of impulses, and we have an impulse response, and how you first flip it in time, and then you move it along the input, and that helps you to generate your output signal, right? This was also very intuitive. And then there was a difference, okay, with zero padding and without zero padding. So with zero padding is the normal thing. That's what we generally use for convolution. And then we came to the concept of correlation or cross correlation. So where the use of cross correlation is to find similar segment shifted in time. For example, I say, I will give you a practical understanding of this. Let's say I say, okay, I'll give you a very gross kind of example. I say hi, and then there is a long audio recording, and I'm saying so many things, like I'm giving a lecture, and then suddenly I say hi, and then again I start speaking something else. So I want to find where is the hi in this long audio recording. So I have my short snippet of hi, and I want to find where is the snippet in that long audio recording. So what I can use is I can use cross correlation. I will take the snippet, I will scan it along the entire long audio recording, and wherever the cross correlation is large, that is potentially the place where I get a perfect match, right? So this is a very gross example of cross correlation, but I hope this will be helpful for you to understand. So Yash is asking, is it like pattern recognition? Yes, it is like pattern recognition. Actually, this is the concept which is used in, if you have heard of convolutional neural networks, CNNs. So it is like pattern search or pattern recognition. But the basic mathematical operation which is working at the root is cross correlation. One question is, could you please explain padding a little mathematically? Okay, what is the meaning of padding? Okay, let me explain from here. Padding just means you add some zeros in the signal. For example, this is a, okay, consider a signal is like a vector. So this is a vector of length, how much length? 0 to 15, so length 16, right? This is a vector of length 16, and this is a vector of length 4, 0, 1, 2, 3. So vector of length 16, vector of length 4. Now if I want to multiply this with this, so that the 3 multiplies with 0, and that's so on. So I cannot do it because I do not know what is the value of x at -1, -2, -3, right? Those values are not known to me. So what I do is I do a zero padding. I will add a 0 here, 0 here, 0 here, so that these 3 values are 0. Now I can do a multiplication of these two and sum all their outputs. That is called zero padding, right? My original vector of length 16, but I add some zeros in the beginning. I add some zeros in the beginning so that mathematically the multiplication is possible, right? If I want to say h of 0 multiplied by x of -3, let's say here m is -3, and I want to compute y0. So my m has to be also, okay, let me think. No, m is -3, so here m is also -3, and n has to be +3 then. Okay, let's say if n is 0 by 0, I have to multiply x of -3 with h of, okay, sorry, this y is -3. So okay, my n is -3 here. If my n is -3 and my m is 0, 0, then okay, no, sorry. If my n is -3, my m has to be plus, again -3 for h0 to come. If I want h, this is flipped, so h0 will multiply, h0 will multiply with, oh sorry, this is cross correlation, I'm sorry, I'm confusing it with convolution. Okay, for cross correlation, here my h of 0 has to multiply with x of -3. So my h of 0, so n has to be +3. Okay, so means n has to be -3, m is -3, so that they become 0, and again m is -3. So my x of -3 multiplies with h of 0, and I get y of -3. Sorry, yeah. So this is the right understanding. So to get my y of -3, I multiply h0 with x of -3. So m is -3, n is also -3. Is that clear? So that is the concept of zero padding. Because I do not know the values of x of -3, -2, -1. So I assume those values are 0. So I increase the length of the vector in this direction by zeros. Another question is, length of high should be same as the length of original signal high. Piyush is asking, yes. So when I gave you the example of I speaking a short snippet high and the long audio recording which has high somewhere. So I told this is a very gross example, but yes. So this is assuming so many things. It is assuming that these signals are exactly matching. Generally, in real speech, it does not happen, but we transform it into some other domain, let's say spectral domain, then it becomes more or less possible. And then the length has to be same, yes, in this example. Yes, so in real world, if I say hi and another person is speaking hi, those signals won't match exactly. That's why I said this example is not the best in real world, but it helps you understand so many things. Okay, assume that this is a string of text, right? Assume this is a string of text, which means the signal is like h corresponds to some number. When I say hi high, I corresponds to some number, and these numbers are written. So assume, let's say these are binary numbers or some. So basically these are strings, not speech. Then it will exactly match, right? Happy with this example? Okay. So yes, so assume that I'm doing string matching, not the audio waveform matching, because audio waveform will have lots of variations. And of course, in this course, we will see how to transform the audio into some representations which match better. So that will be a part of this course. But for the simple example, consider strings matching. Okay, this was the concept of cross correlation, which is used for finding the blobs or snippets in a longer segment, where the blob is of shorter segment. Okay, so we studied in this lecture two topics: convolution as well as correlation. Any questions? Another question by Naman. Cross correlation gives us a vector. If so, then how do we recognize high correlations? Okay, I can request, if you don't mind, if you don't want to reveal your identity, you can write the comment to everyone so that everybody sees your question. So no need to send me privately, no problem. But if you have problem, if you want to keep your name anonymous, then only send me a private message. But if you are all right, then I would recommend send a message to everyone so that everybody can see your question. And these questions are good questions, so no need to be shy. Okay, so question is, cross correlation gives us a vector. If so, then how do we recognize high correlations? Good question. So this, okay, there is something called correlation coefficient. Okay, without going into that, if you just look at relative measure, let's say I'm this my snippet is there and the whole signal is there. If I'm scanning my whole signal with this snippet, and if I can do a relative comparison, wherever is the largest peak, that is the point of best match, right? And you have to look at the magnitude, because it is possible that this signal is exactly the flip version, the negative version of the one in the long signal. The snippet is the negative version of this. So in the the correlation will be exactly minus the largest value. So you look at the magnitude plot so that the magnitude is largest, there the correlation is largest. Okay. And of course, there are some other statistical measures like correlation coefficient, etc., which do some kind of normalization that, okay, it normalizes over the length or the variance of individual signals so that you get a value between, I think, -1 to +1. So those measures are also there, correlation coefficient. But I'm trying to give you an intuitive understanding of correlation. Whenever you read the word correlation, try to think it in terms of two signals are matching. If they have high correlation, means they look very much similar. And if they have low correlation, it means that they are not very similar. And this concept is very useful for pattern recognition. Actually, I think this concept of correlation can be seen as dot product of two vectors. I will show you many more interpretations of correlation in the subsequent videos, especially in the machine learning part. So neural networks, etc., whatever operations they do, mostly they depend on correlation. Okay, and convolution is about one system. It has some input, some output, and if the system is linear time invariant, we can represent this system, or we can characterize this system with an impulse response, and we can use that impulse response to construct the output for any input, because any input can be represented as a series of impulses or a series of Kronecker delta functions. Okay, so that was about the fourth chapter, fourth lesson or lecture. And these are some good references. You don't have to go through all these, all the chapters of the book, but chapter 2 is good if you want to read in the Quateri book. And in Signals and Systems, Fourier Transforms are explained. And this is there are nice blobs and nice videos like Tutorial Point. They have got some nice blob on DSP, some nice write-ups on DSP, which you can go through. Okay, let me go to the lecture number 5 now, which is about Fourier transforms. So any periodic signal, if you have any periodic signal. So if I ask you the question, what is the period of this signal? What is the period of this signal? Or T naught. T naught means the period after which it repeats. After how many samples it repeats. You can write on the chat window the answer. 15. Think carefully. 10. 10. Okay, 10. Yes. Good. Yes, 10 is the right answer. So it starts from 0, and at 10, you again see the same value as 0. And then subsequent values are just repetition of these values. So yes, the period is 10. So basically you add this, you add 10 to this, you again get the same pattern. Right? So the signal repeats itself after every 10 time steps. So the time period is 10. And similarly for this one again, on the right hand side again, the period is 10. But this signal looks very different from this signal, but they both have same period. Okay. Now, what is the fundamental frequency F naught? So you know T naught is 10. And what is F naught? Please don't write on the board. Just disable attendee annotation. Okay. Okay, so what is the fundamental frequency F naught? You know T naught, 1 upon T naught is basically F naught. Here T naught is simply 16 because it repeats after every 16 time steps. Okay, now how do I find the periodicity? How do I find the time period, or the time period of the signal? So the answer is, looking at the signal, yes, we can find out. But if I have to find programmatically, if I want to write a script, given any signal, it will tell me what is the T naught for that signal. So how will you do that? So a very simple way to do it is autocorrelation. Now see, we are using the concept of cross correlation, right? If we have this blob and I want to find where does this blob occur in the signal, of course it will occur in the at zero shift. If I have two same signals, and at zero shift they will be matching exactly, but since it's a periodic signal, it will also match at some non-zero shift. If I make a non-zero shift, again they will match at some point, and wherever the first match again, that will be the point of when the signal starts repeating. So that gives us the time period of the signal. Is this concept clear? So that is why you see here, you get a peak at 16, right? A peak at 0 because the signal is exactly overlapping itself, and then a peak at 16 because when you shift them, again the overlap happens. This is the concept of autocorrelation, and how do we use cross correlation to find the periodicity of a signal. Now we are going to look at another way to find periodicity, and for that we have to first learn the concept of Fourier transforms. So decompose the signal. We can decompose any signal. It's a periodic signal. We can decompose into sinusoids, which are also periodic with the same period or multiple of that period. With the same frequency or multiple of that frequency, or with the same period and the integral factors of that period. Like this is let's say this is T naught. This is T naught is 16. Let us say this has a period of 16. This has a period of 16. Sinusoid of period 16. Sinusoid of period 8. Sinusoid of period 4. Sinusoid of period 2. Sinusoid of period 1. Like that. all the integral factors of that period, all those sinusoids can come together to create that signal exactly, if it is a periodic signal. Okay. Let's do an analysis. Okay, periodic signal can be represented like this: some amplitude times sinusoid of 2 pi, some frequency n plus some phase. And I can represent it in the exponential form also. Then phase can be ignored because the phase can be merged with the amplitude itself. Amplitude becomes a complex number then. And you get some amplitude, which is a complex number, x naught times exponential of 2 pi f naught n times j. Exponential of j 2 pi f naught n, right? So, okay, this is the thing. My fundamental frequency is k upon capital N. As I told you that I can represent any periodic signal as sum of sinusoids. And these sinusoids are these, where the frequencies are integral multiples. Our question is, why we only use sine and not cos? Sine and cos are related, right? If I, the phase, it's just related by a phase shift. You introduce a phase shift of pi by 2, it becomes cos. So both are equivalent because this phase shift is general. So by changing the angle appropriately, you can convert this entire notation into cosine or cos. So both are equivalent. Okay, now let's come to the concept of Fourier transforms. Now here we get rid of the sine and cos confusion and we use exponential of j theta, so which has both sine and cos within it. And if you take the real part of this, it is a cos. If you take the imaginary part of this, it's a sine. So we work with the complex numbers, and whenever required, we can move back to our sine or cosine domain. Okay, so let's say this is a signal, and if we multiply with exponential of minus j theta, then we get the Fourier series. I think you have read all this in your basic signals and systems courses. I have spent some time in the videos to explain these things, but what we need most in this course is this discrete Fourier transform. So basically, what is discrete Fourier transform? You have a signal xn, which is finite. You see, it's a finite signal, 0 to n minus 1 only. That is the length of the signal is capital N. That is it. Now I can convert it into a discrete Fourier transform of the same length. And so this xn is assumed to be periodic, and this xk is also assumed to be periodic. Basically, we just work with one window, and we assume that this window repeats over and over. And similarly, this Fourier transform domain also, we work with one window, and we assume that this window is repeating over and over again. So my xn is discrete and periodic. My xk is also discrete and periodic. If you remember this small figure, whenever my one domain is continuous, the other domain will be aperiodic. Whenever this domain is discrete, the other domain will be periodic. So basically, as we told, sampling introduces copies. So whenever you sample, you go from continuous to discrete by sampling. Immediately, your other domain, the transform domain, will become periodic. Let's say this thing, the copies appear up at appropriate gaps. Okay, and then we saw that how the properties of discrete Fourier transform, that if my xn is real, because in this course or in real life, we mostly work with real xn. So let's say it's an audio signal or any sensor data, they're all real signals, right? So their Fourier transforms will be, the magnitude plot is an even function and the phase plot is an odd function. So that is the thing. And since there is periodicity, so we get symmetry. My xk will be even and as well as periodic. So what I get is a symmetric function. My xk is a block of length capital N. So from 0 to n by 2, one pattern, and n by 2 to n, another pattern with a flipped thing, so that they are mirror symmetric to each other. Okay, now this is an important concept. If I give you a signal and I ask you, you take a Fourier transform of this signal, and where will the peak occur? The peak will occur where the peak in the magnitude plot occur. the peak in the magnitude Fourier transform will be appearing whenever you go back to the basic definition of your xk basic formula and see wherever they match each other. Basically, if my xn is j2 pi 2 upon 32 times n, and this term is j2 pi again 2 upon 32 n, then you see they exactly match each other. They cancel out. I get summation over n of 1, and it becomes a very large value, right? So basically it becomes equal to capital N, 32. So when does that happen? It happens when my k, small k, is equal to 2. Right? Basically when my k upon capital N is equal to this number, then that happens. So that's it. And if there are multiple peaks, then at these multiple places, that same thing is happening. So this is 2 upon 32 will be equal to k upon capital N. Capital N is 32 here. So k is equal to capital K is equal to 2. And then 8 upon 32 is equal to k upon capital N. Capital N is 32 here. So 32 can get cancelled out, and we get a peak at 8. So at k equal to 2 and k equal to 8, the peaks are appearing. And what are these peaks? Because as we just now discussed, that they are mirror symmetric to each other. So the peak will occur also in the other half. So in the left half, the peaks are appearing, and similarly, because of mirror symmetry, the peaks will also appear in the right half. So this peak is at 2, then there will be peak at -2. But -2 is not possible because we are just looking at one window of 0 to 31, and then you take your you add 32 to this number. So -2 plus 32, it becomes 30. So I get a peak at 30. Okay, and then the concept of zero padding. It's a very visually you can understand it very easily. And if I have a zero padding here, I can take my NFFT to be large. My NFFT can be now 64 or 128 or even 1024, no problem. Basically, I just have to keep adding zeros wherever I don't know the values. So this is with zero padding. Now, what is the advantage of zero padding? I will get a higher resolution. You can see at NFFT equal to 16, I so poor resolution of my spectrum or my Fourier transform. But with a higher NFFT, I get much more resolution. The graph becomes much more sharp. Okay, so a very nice question coming up here, that in this previous thing, there is an error in the image that the peak is not occurring at 30. Peak should have appeared at 30, right? Because this is 2. So 2 and -2. If I add 32, so it becomes 30. So peak should have appeared at 30, but the peak is appearing here at some other value. So when I did this plotting, I did not realize I did a small mistake. The length of the signal is not 32, but the length of signal is 33. And my NFFT also becomes 33, because of which things become a little messy here. So it becomes 33 minus 2, which means 31. That is why you see a peak at 31, because my NFFT is 33 in this plot. Although in the analysis, I tried to keep it 32, but in this plot, by mistake, it became 33 because the length of the signal was 33. And I used the length of the signal as my NFFT. So please excuse me for this small mistake here. But if you do these plots yourself with the proper capital N and proper length of xn, then you will find the peak appearing at 30. Does that clarify? What is NFFT? NFFT is the capital N which we used in my discrete Fourier transform. Let me just show you. Okay, so this capital N, this is NFFT, the capital N of FFT or DFT. So this capital N is in my hands. I can choose it whatever I want. And this need not be same as the length of the signal. Right? I showed you here that my length of the signal is how much here? I think it is 32. Length of signal is 32, but my NFFT could be 16 or 32, 64. Basically, when it is 16, I will only consider 16 samples here, and I will have to ignore all other samples. When it is 32, then I'm considering all the samples, When it is 64, I'm considering all these samples plus the zero padding. And if it is 128, I'm considering these samples plus the longer zero padding, right? So generally, you never do an FFT of 16. Why? Because you have to ignore these values. You have to ignore half of your signal, which you don't want to ignore your signal. So generally, we never take an FFT smaller than the length of the signal or smaller than the length of the window. But we can take an FFT larger than the length of the window. That is always allowed. But we never take smaller. Okay. I think I'm telling many points which are not there in the slides because these are very practical points, and I hope you note them down properly, and they are important for this course. Whatever we are discussing, that is important. Okay, now if you want to use Python, DFT in Python, you can do FFT or inverse Fourier transform, everything using these commands which are there, and the documentation is there. Or just go to Google and put NumPy FFT or NumPy DFT. You will get to this link. Yes, so now what is the use of FFT? Mainly it is used for correlation analysis, periodicity analysis. Signal is periodic. What is the frequency of the signal? What are the prominent frequencies present in the signal, and things like that. Other uses are like for compression, data compression, for sinusoidal representation. That's fine. Yes, so we studied in this lecture about periodicity and Fourier transforms, and these are the same references. Now I want to show you something interesting. I want to show you some programming which you can do. Audio waveform. I will share this PyNB file also with you. Okay, this is a programming course, so we'll be focusing a lot on programming aspects. So I hope you are putting a lot of time in understanding the programming aspects as well. So whatever we discussed in these lectures, I'm now going to present the programming aspects of those. How do we program them? Some ways. And I would also you will be getting an assignment this week, which will be programming based assignment. So please do it nicely, and that will help you to understand these concepts better. Let me first show you the folder. Okay. Okay, so there is an audio file here. I'll just play it for you.
Hari.
Can you hear it?
Hari. Hari.
Yeah, so it simply says Hari. So this is just an audio file which I recorded just for this purpose. Now I want to read it into my computer. So I will just go to Google and put how to read audio file in Python. And one simple way is, okay, so two very basic libraries which are used in Python are NumPy and SciPy. NumPy and SciPy. So NumPy you have already seen. SciPy is another library which has got some important useful utilities like how to read audio files, etc. So this is for reading a wave file. There is a function called wavefile, or a library called wavefile in scipy.io. IO generally means input output. So this is an input output library. So it is used to read and input audio. So I want to read this hari.wave, which is in the same folder as my script. My script is audio waveform.ipnb, and my audio file is hari2.wave. So I will just say wavefile.read hari2.wave. And what it reads is sampling frequency and the signal. So I want to see what is my sampling frequency. So, oops, I have to run this and run. So my sampling frequency is 44,100 hertz. So which means for 1 second of audio, I have got 44,100 samples. Now I want to see what is the length of X. My signal X. It's 42,754, which means it is approximately 1 minute 1 second long. It is approximately 1 second long, slightly bigger than 1 second, because I get 44,000. So it is slightly less than 1 second. 44,100 is the number of samples in 1 second. So my X is slightly shorter than 1 second. So this is how I read my audio file into my computer. Now this is a waveform. This is a time series. How do I analyze this time series? So let me start with plotting, because that is the thing which gives me the best intuitive feel of what is happening. I just take a signal and plot it. So plot the waveform. So for plotting, I am using matplotlib library, and this matplotlib library has got pyplot module, which has got the PLT thing, and pyplot, which I have nicknamed as PLT. So pyplot is being used here. So what I am doing here is, okay, I have my X, which is the audio signal. Now I am creating an array of timestamps corresponding to each sample. So I know what are the units of these timestamps. Here, this is just the number of the sample index, right? These are just the sample indices n. But I want to make it as time in seconds. What will I do? I will just divide it by fs. This is t in seconds. Now, if I do plotting now, what do I get? Okay, so I get now this plot where my x-axis is the time in seconds. So from 0 to, you can see it is slightly less than 1 second. So this is how the audio waveform looks like. So this is how I plot the waveform. Now, convolution. Let us try to understand the concept of convolution. To illustrate this concept, okay, first of all, how do we find convolution in Python? So there is a simple function called convolve in NumPy library. NumPy library you are familiar with. It's very common and very useful library for any matrix or vector operations. Now this NumPy library has a function called convolve, and I am first extracting a small x. This x. So what I did actually, how did I find this out? So I just plotted my x with samples, and I found that approximately at 20,000, I have some non-zero values. Let me extract a small snippet from this area. So I extracted a small snippet from, you can see my h is x going from 20,000 to 20,500. So what is the length of the signal? The length of the signal will be 500, right? So the length of this signal will be 500. You can see 0 to 500. But I want to downsample it, or I want to use, I don't want to take one value at every sample. I want to get after every five samples. Now you see the length reduces to 100. So you see the length is 100 now. So basically I'm picking samples at intervals of 5, so that my sampling frequency is reduced 5 times. Okay, so this is just for, I can also make it even smaller, but that is all right. Just to make the array length smaller. Okay, now I took another, my x. This is a numpy.0. It's a zero thing, and at n equal to 10, I am introducing an impulse. So what will happen if I do the convolution? Then this same x pattern, this h pattern, will be shifted by 10 timestamps, by 10 samples, right? Because I'm just introducing a delay, and that's what is happening here. So this is the concept of convolution. And how do I convolve? I use numpy.convolve xx, which is basically an impulse at t equal to 10 or n equal to 10, and h is my impulse response. And mode which I use is full. Generally for convolution, I use full mode because I want to get, I want to preserve my, yeah. Basically I assume that signal is 0 outside the windows, which is not given. Okay, now let's come to the concept of correlation. Correlation is also implemented for you in NumPy. So if you just put NumPy correlation in Google, it will give you, it will add, take you to this link, and this link is this is the documentation of NumPy, which has correlate function. Now, what I'm doing is this is my x1 as I did above. Now, what I want to do here is I want to do an autocorrelation. Autocorrelation means I want to find the periodicity of this signal. This is a periodic signal, right? Or not exactly a periodic signal, but approximately a periodic signal, right? I want to I want to estimate the time period of this periodic signal. As I showed you in the third lecture, I think that time period can be found out with the help of autocorrelation function. So here I'm doing an autocorrelation. So basically np.correlate. So I am adding some zeros. The x1 is the longer signal. So I take this same signal and add some zeros at the back. And then again x1, which is the same signal. And the maximum will occur at 0 because they will match exactly. But if as I shift, because there is periodicity, whenever it hits the periodic time period, it will again shoot. That's what I'm seeing. It is shooting here, which is approximately, let's say, 33 or something, 33, 35, right here. And what I find here is, what is the periodicity of this? It is approximately, you see, 0 thing, it will be somewhere here. It is approximately 33, right? So yes, so my autocorrelation function is able to give a good estimate of periodicity. Now what I want to do is, another way of finding periodicity is the Fourier transforms. So I take a Fourier transform of x1. What I find here is, okay, first of all, I'm printing the length of x1, it is 100, right? Because we took 500 samples with a gap of 5 in between. So my length of x1 is 100. Now I'm plotting my, okay, capital X1. What is capital X1? Capital X1 is the Fourier transform of x1. Small x, Fourier transform is capital X. So np.fft.fft x1. This will compute the Fourier transform. But this Fourier transform is a complex number. To plot, I want to plot the magnitude of this Fourier transform. That is why I'm using np.abs, which means the absolute value of x1. And I don't need this actually. Oh, x1 is not defined. Let me define it first. Okay. So if I take the Fourier transform, what I find is I get a peak. So which means that periodicity is there. Some fundamental period is there. Some small spurious peaks are there, which I wouldn't consider. But some very prominent peak is there, which I would like to consider. Now I want to see what is the periodicity of this signal. Periodicity of this signal. For that, I have to find out what is K naught. Let me show you actually first. Okay. Okay. So if the peak is appearing at K naught and NFFT is capital N, then what is the time period of that signal? I can say K F naught or T naught. What is the T naught? What is the time period of that signal? If in the Fourier transform, an n-point Fourier transform, I get a peak at some K naught, then what is the time period of my original signal? To find that, let me go back to the original definition of Fourier transform, DFT. So my DFT is xn times e to the minus j 2 pi k upon capital N times small n, summed over all small n, right? This is my original definition of xk. Now, the peak of the magnitude will occur when both of these terms approximately cancel out each other. So when will that happen? That will happen when this numerator, sorry, these terms in the exponential, they are exactly same and negative of each other. So what I get here is, if I do this comparison, so 2 pi upon T naught is equal to 2 pi K upon capital N. So if they are same, this means 1 upon T naught is K upon capital N, right? Now let's go back to our example here. So what is my K naught here? What is my K naught here? So it is somewhere here. I don't know what is it. So what I will do here is I'll plot it partially because I want to see where is this peak appearing. I know it appears somewhere between 0 to 20. Let me say 0 to 20. So I'm plotting only between 0 to 20. And I find that the peak appears here. Still, it is not clear what exactly it is. I will make it in. Yes. Now, if I make it 10, it is very clear that the peak appears at 3. The peak appears at 3. So my K naught is 3. Now, if my K naught is 3, what is my capital T naught? My capital T naught will be from this formula. Capital T naught is capital N upon K. So what is capital N? Capital N is 100, right? Length of x1. So if I don't give any specific n here, it will be length of x1. So my capital N is 100 divided by K naught, which is 3. Right? Capital N divided by K or K naught, which is 3. So it is approximately 33. And that's what we found above as well, that the peak of autocorrelation also appears approximately at 33. And the peak of Fourier transform also appears corresponding to time period of 33. Right? So I think that was the content of this week. If you have any questions, please ask. Now, we have 5 more minutes to go, but I would request you to ask for questions. Next week, we'll be reading about spectrograms, short-term Fourier transforms, and spectrograms. So, but if you have any questions regarding this week's content, please ask questions, and you will get assignments soon. The first assignment will be very easy. It will help you to um, learn programming first of all, and then it will help you to learn the concepts which you have learned here in this course. Okay, now I would request all the students who are not very familiar with programming before, please spend time with programming, because this course will be heavily programming dependent. So learn programming and practice programming through these. I'm sharing with you IPython files. I'm giving you material which has got a lot of programming stuff. I'm giving you codes as well. So use all that to learn programming so that you are very comfortable with Python programming. And this will be very helpful for you in your whatever research or anything you are doing. Okay, so there is a question from Rudrasen. He says videos can't be downloaded. So we are uploading the videos on YouTube as well as on Mookit. You can watch them from there, right? From YouTube as well as Mookit. Okay, now the Yash Kumar is asking, where have we defined x1 length as 100? Okay, no problem. Good question. So you remember we extracted my x1 here. Okay, this is h. Similarly, x1 was extracted here. Yeah, x1 was x from index 20,000 to index 20,500 with a gap of 5. So which means how many instances come? It's 500 divided by 5, so 100. That is where we define x1 length as 100. Okay, thank you, Yash. Now, Jason is asking, use vget extension to download in embedded videos. Videos are on YouTube too. Yes, so videos are there on YouTube as well. You can go to our Madhav Lab page, and the playlist is created with this course name, MLSP 2020. You can go to that playlist and watch all the lectures there. But I would recommend you to watch on Mookit because we may use the Mookit analytics to see how the students are doing, how many are watching lectures, how many are not watching lectures. So I would recommend you to go through Mookit platform or hello.iitk platform rather than directly YouTube. But if you have problems, then do let us know. if you know, because I don't think it should be a problem, because MOOCit also uses YouTube backend, so the speed should be essentially the same. If you're able to watch it in YouTube, you should be able to watch it in MOOCit as well. Anyways, I leave it to you. You Okay. Actually, what you can do is you don't have to download the. If you have a mobile phone, I don't know if laptops allow that, but in mobile phones, you can also download YouTube videos. You can download and save it for later. Basically, you download the YouTube video on your mobile phone. It is downloaded and kept there for, I think, 1 month. But if you reconnect to internet, it will stay for longer. Basically, 1 month of inactivity on YouTube. So it will keep the videos for 1 month uh, when you don't use YouTube on that mobile at all. But if you're using YouTube on that mobile, then the videos can stay forever, whenever YouTube, until whatever time YouTube allows. So I think that's a good way. You download the video on your mobile phone on the YouTube itself and then watch it. Any other questions? If not, then we can stop here. Okay. Thank you very much.